Hi class, today we would like to learn about IIR filter design by using bilinear transformations, BLT. IIR filter design by BLT. BLT is bilinear transformation, is one-to-one mapping from the S domain to the Z domain. BLT is a conformal mapping that transforms the J omega exists in analogs into the unit circle in the Z transform only once, which is in digital. Thus, it avoids the aliasing of frequency component. So all the points at the right-hand plane S will map inside the unit circle of Z plane, and all the points in the right-hand plane S will map outside the circle of Z plane. Okay, for example, we will have the X plane with the x-axis of sigma and J omega at the y-axis. Okay, this one is our X plane. And then we will have another plane is our Z plane. So we will have our real parts and our imaginary at the y-axis. Okay, so we will have a unit circle at our Z plane. Okay, so when the point at the right-hand plane, it will map inside the circle. For example, it will have the point here at the left-hand plane, so it will map into the circle. For example, when we have the point at our right-hand plane, this blue point at our right-hand side, then it will map outside the circle. So it looks like this. Consider the analog linear filter with a transfer function Hs equals to B divided by S plus A. And our Hs is our transfer function where Ys divided by Xs. Ys is our output, Xs is our input. So we multiply cross Sys plus with Ays equals to Bxs. After that, we take into inverse Laplace transform. When we inverse the Sys, we will get the differentiation dyt divided by dt with one s. Okay, Ys, A is coefficient, so we will have A, Y, T, and B coefficient B, X, T. Integrate this above equation between the limits of n t minus of t and n t. So now we integrate it from the nt minus t until nt for all three components. So generate equation 1. After that, we have to recall back our trapezoidal rule for the numeric integrations. So integrate the nt minus of t until nt. We will have ht dt, and this ht dt is equals to t divided by 2 h nt plus with h nt minus of t. Equation number 2. Now we apply the equation 1 and 2 together. So from the equation number 1, we have integrated nt minus t until nt for the differentiation dy, t divided by dt, and also integrate for our ayt and integrate for our bxt. Then we substitute the equation number 2 into 1. So when we integrate the nt minus t until nt, dy t divided by dt, we will have y nt minus of y nt minus of t because of integrations with the differentiations. Okay. Then we plus with our a. This time we will have a yt. We integrate our yt. We will have, using the trapezoidal rule, we have t divided by 2 y nt plus with y nt minus of t. And then we integrate our bxt trapezoidal rules. So we will have t divided by 2 x nt plus with your x nt minus of t. After we get these equations, we collect the same ynt and the ynt minus t together. So we are collect here, and this at divided by 2 ynt and plus with the at divided by 2 ynt minus of t. Okay, this one we expand it inside for each one. Okay, same for the bt divided by 2, we also expand it each one. So we get this equation. After that, we arrange all the n t together, y and t all together, and y and t minus t all together, and also x and t minus of t. Then we factor out the same y and t, so we will have 1 here plus with our at divided by 2. And then here also is 1, so it's 1 minus of at divided by 2. So this one is minus. Here is positive, we take out, so we get minus, here also minus. So we get positive. Okay, bt divided by 2, x and t plus with our x and t minus of t. After that, we let this equation yn equals to y and t, xn equals to x and t. Okay, so this y and t will become yn, y and t minus of t will become yn minus of 1, x and t will become xn, and x and t minus of t will become xn minus of 1. Okay, after that, we take into z transform for these differentiation equations. So yn into z transform is yz, yn minus 1, we will have z minus 1 and yz. For this one, we will have 1 plus with our z minus 1 and xz. After that, we factor out this yz and this yz. So we factor out here. So we get 1 plus at divided by 2 minus of 1 minus of at divided by 2 bracket and z minus 1. We bring forward the yz divided by xz, and then we will get this bt divided by 2 will be divided by this one. So we will have hash z equals to yz divided by xz equals to bt divided by 2 bracket 1 plus z minus 1 and divided by 1 plus at divided by 2 minus of 1 minus at divided by 2 bracket z minus 1. After that, we expand the z minus 1 into the equation. We will get this equation. Z minus 1 minus of at divided by 2 z minus 1. Okay, and then we expand this minus inside the equation. So we get minus and plus. Okay. After that, we factor out, we collect this 82 and this 80 divided by 2 z together. So we can factor out 80 divided by 2 z plus z minus 1. Okay. So we have these equations. After that, we want to divide the numerator and the denominator so that it will have the same denominator. So what we do is we multiply above with 2 divided by t 1 plus z minus 1 and divided by 2 divided by t 1 plus with z minus 1. We multiply inside the equation. So for the above, we can cancel off this one and this one. And t, we cancel off with t. 2, we cancel off with 2. So we left with b. For the below, we have to cancel off these 2 and these 2 here. And for this one, z 1 plus z minus 1. It will need to be multiplied inside. So we will have t 1 plus z minus 1. And here we have 2 and 1 minus of z minus 1. And plus with our a. So by compare with the equation 0, which is hs equals to b divided by s plus a. And now we know that this is our s. So our s is equal to 2 divided by t multiplied with 1 minus of z minus 1 minus divided by 1 plus z minus 1. We can simplify this s by divide by convert this z minus 1 become 1 over z. And then we can simplify it to 2 divided by t, z minus 1 plus divided by z plus 1. Okay. Now we go for the generate characteristic of your matrix. So we have the z is equals to exponential st. This is the general characteristic. Okay. So by obtain, we substitute this as equals to our sigma plus with j omega. And we also have expressed in the polar form for the z is equals to r, real parts or real, exponential j omega. Okay. Now for this equation, we substitute the z with r exponential j omega and r exponential j omega. After that, this exponential j omega actually is equals to cos omega, okay, plus with our j sine omega. So we just put inside the equation, so we get r cos s w omega minus of 1 plus with our j r sine omega divided by our r cos omega plus with our 1 plus with j r sine omega. Okay, then we multiply it with our conjugate. This is our conjugate. After we multiply with our conjugate, we will get this equation, r square cos square omega plus with r square sine square omega minus 1 plus with j 2r sine omega divided by r cos omega plus 1 in bracket square plus with your r square sine square omega. Then after that, we will have the r square cos square omega plus with your r square sine square omega minus of 1 and plus with our j 2r sine omega. So we still remember our cos square omega and plus sine square omega is equals to 1. So we substitute this in this equation, we get r square. So for here, we will obtain r square. Okay. So for the below, we will have also same 1 minus of r square. So this part and our this part. So we get 1 plus r square plus with our 2r cos omega. After that, we separate it into the real part and the imaginary parts. So from here, we can see this is our real part. This one is our imaginary part with the j. So our real part is compared with our s equals to r. So this equation, we will compare with our s equals to sigma plus with j omega. So our sigma is our real part. So this sigma is equals to 2 divided by t multiplied with r square minus 1 divided by 1 plus r square plus with your 2r cos omega is our real part. And then we do for our imaginary part, omega equals to 2 divided by t and 2r sine omega. And this omega is our digital form in digital. And this omega is in analog. Okay, the shapes look like the A, which means is analogs. So we have 2 divided by t, 2r sine omega divided by 1 plus with r square plus with 2r cos omega is our imaginary part. Okay, so actually we have 3 cases. The first 2 cases is the stable digital system. So where our left-hand side of our explain is mapped on the point inside the unit circle of the z-plane. So when we have r is smaller than 1, your sigma also is smaller than 1, it will substitute in the real part only. Okay, for example, we have this equation, this plane. So now our r is smaller than 1. So our sigma also will be smaller than 0. So here is our sigma. So which means our sigma is in negative. Okay, so the radius is smaller than 1, the r. So it will map into the z-plane inside the circle. Okay. So when we have our sigma is bigger than 0, so for example here, sigma is bigger than 0, is a positive value. So your r is bigger than 1. So your r is bigger than 1, it will map into here. So it suit into the real part only as well. So this above one is our x-plane, below is our z-plane. Okay. For case 3, unity magnitudes, where we have a unity magnitude of r is equal to 1. So for this case, we are using green color. So our point is on top of the 0. And then it will map into the r equals to 1. So we will consider it as the imaginary part. So we will have omega analog equals to 2 divided by t. Okay, 2 here. Now our r is equals to 1. So substitute r with 1. Sine omega in digital divided by 1 plus r square. R is 1 square plus with 2. R is 1 cos omega. Okay, so we get the answer is here 2 over t, 2 sine, 2 plus 2 cos omega. And we simplify the 2. So we get sine omega divided by 1 plus cos omega multiplied with our 2t. Okay, now this sine omega actually we can using the trigonometry formula, we'll get 2 sine omega divided by 2 cos omega divided by 2, and 1 we will get cos square w divided by 2 plus with sine square w by 2, and plus with your cos omega here, so plus with cos omega square w by 2 and minus of sine square w divided by 2. So and this whole equation we can convert it into tangent. So you will get 2 divided by t tangent omega divided by 2. You can simplify it into a tangent. Now we go to the step to design the digital filter using bilinear transformation techniques. Okay. First step, from the given specification, we have to find our pre-wrapping omega frequency, which means is our omega in the shape of analog, like A. So equals to 2 divided by t tangent omega digital divided by 2. Second step, we were using the analog frequency, the ohm, that given to find the HS of our analog filter. After that, we will select our sampling rate of our digital filter, known as t in second per sample. Step number 4, we will substitute our equation S equals to 2 divided by t multiplied by 1 minus of z minus 1 divided by 1 plus z minus 1 into the transfer function that we found in step 2. Okay. After that, we will obtain our H, Z, which means is our digital transfer function. Okay, so don't waste the time. Now we go for the example. Example 1. Convert the analog filter with the system function below, Hs equals to S plus 0.1 divided by S plus 0.1 square, bracket square, plus week 16. So turn this one into a digital IIR filter by using the bilinear transformation method, and the digital filter have a response frequency of omega R is equals to pi divided by 2. Okay, first step, we have to find the omega C, the pre-wrapping analog frequency. Okay. Second step, we have to find HS. For this question, they already given our analog filter transfer function, which means our HS is equals to S plus 0.1 divided by S plus 0.1 square plus with 16. And the question also given omega R resonant frequency for the digital is equals to pi divided by 2. Okay. So we compare our equation HS with the original one, S square plus with S plus A plus with S plus A divided by S plus A square plus with our omega C square. So from here we can compare our equation. We obtain that omega C square is equals to 16. So omega C is equals to 4 radian per second. Okay, we done for our step 1. And step 2 is given. Then we go to step 3. Step 3 is find the sampling periods, our T. Okay, now we know our omega C is equals to 4. So we just put inside. And we know our omega is equals to pi divided by 2. And then we divide again with our 2 to in this equation. So we calculate it. We will get our T is equals to 1/2 seconds. After that, we will go for step number 4. To find our Hz by using the bilinear transformation. So Hz is equal to HAS, and our S is equals to 2 divided by T multiplied with 1 minus of Z minus 1 divided by 1 plus Z minus 1. Okay, so in this case, HAS, we just put in our equation S plus 0.1 divided by S plus 0.1 square plus with 16, and also our S. And then our T, we substitute in a 1/2 in here. Okay, so here 1/2, so we'll get 4. 2 divided by 1/2, we get 4. So we have 4, 1 plus Z minus 1, 1 minus of Z minus 1, 1 plus Z minus 1, and plus with our 0.1, same for S here. So we just substitute our S into with this equation. Okay. After that, we expand the question with the same numerator. So this one. Okay. Then we expand again. 4, you will obtain 4 multiply 1 minus of Z minus 1 plus with 0.1 multiply with 1 plus Z minus 1 divided by our this one, Z plus Z minus 1 and the below. So this one, this and this can be cancelled off. So, and then we multiply it. So we will have 1 plus Z minus 1. We will multiply the numerator and our divide with our denominator. And then we expand it. We will get, for this part, we expand it. We will get 4.1 minus of 3.9 Z minus 1. For the below, we also will get the same answer, just power of 2. And then 16 we write back, and here we also write back. And then we expand again for the below denominator, and we expand the above again, so we get the answer in here. After that, we want to make it into the simplest form so that we can draw our realization function, realization form image. So we divide with 32.81. So above we divide 32.81, below we also divide 32.81. By keying in calculator, we'll get the answer in this equation. After we get this equation, we have to realize our transfer function into the direct form 1 or direct form 2. So in this case, we will draw our system into direct form 2. Now we will draw these equations into our direct form 2. So we draw it into direct form 2. For the first, we draw the denominator and then we only draw the numerator. Okay, so we will have an input xn or xz. So we go inside. So first we put one dot. Yeah. Okay, we put a plus here, summation here, and then we go straight. So first is 1, so we put it 1, and then we go down. So we have z minus 1, this one, and then we multiply this thing with 0.0006, and we sum up. Okay, for the next one, we will have z minus 1 and then z minus 2. So we go down again, backwards. So backward, we have to remind this one is minus 1. So if you want to get plus, we have to minus of 0.951. And then it will be sum up. Okay, then we have to draw our numerator. First, we go straight. We will have our first one is 0.125. Okay, and then z minus 1, we will multiply with our 0.006. Then we go, and then we sum up. And then we have z minus 2. So z minus 2, we will have the equation minus here. So this one, straight line is 1 forwards. So we have minus of 0.119. And then we go up, sum up, and we'll go for our output y z. So now we done for our direct form 2 block diagram. Okay, next we go to example 2, question 2 for our bilinear transformation to design our IIR filter. Now we want to design a single pole low pass filter with a 3 dB bandwidth of 0.2 pi. Using the bilinear transformation, we apply on the analog filter Hs equals to omega c divided by s plus omega c. So at here, we have omega c is the 3 dB bandwidth of our analog filter. So which means here we have omega c is at 3 dB bandwidth. So our bandwidth is 0.2 omega. Okay. So we go for the calculations. So we know that our omega c in the digital is equal to 0.2 pi to 4 at the cut-off frequency at 3 dB. First step, we want to find our pre-wrapping analog frequency. This analog omega c. So this one is in analog. So equals to 2 divided by t tangent digital omega c divided by 2. So we substitute our digital omega c with 0.2 pi divided by 2. And we calculate with the calculator, we will get 0.65 divided by t. And then we do step 2, 3, and 4 by using our bilinear transformation. Step 2 is our HAS. So we already given in the question. So HZ, HAS, then we substitute with our step number 4 as equals to 2 divided by t multiplied with 1 minus of z minus 1 divided by 1 plus z minus 1. Okay, so in this case, we substitute our omega c with 0.65 divided by t. Okay, after that, we also substitute our s with 2 divided by t. Multiply with this 1 minus of z minus 1 divided by 1 plus z minus 1. And then in this case, we can cancel off our t. Okay, so we get 0.65 divided by 2, 1 plus z minus 1 divided by 1 plus z minus 1 plus 0.5. Okay, then we multiply above and below with 1 minus of z, that's 1, and 1 minus of z. That's 1. Okay, so we'll get this equation. And then we expand it inside. And here we expand it. And here we also expand it. You will get this equation. After that, we minus off here and here, we get negative 1.35. Here we sum up 2 with 0.2, 0.65, we get 2.65. And then in here, we divide with 2.65 above, and below also we divide with 2.65 because we want to get the simplest function so that we can draw our relaxation system. So for this question, it's very simple. We can draw our direct form 1 and direct form 2. So we can draw our direct form 2 with the equation here. So first, we start with 1. So we start with our xn input, sum with our 1. Then this 1 will go down for our z minus 1. And then here we multiply with our 0.509. And we go up with sum up. And for the upper, we will have 0.245. There's a summation here. And here is our y and output. Okay, so here we will have another one is our z minus 1 multiplied with our 0.245. And then we sum up. That's simple. Done for our relaxation parts. Okay, lastly, we want to compare the similarity and the differentiation and the difference between AD, approximate derivative method, impulse invariant method, IIM, and also bilinear transformation, BLT. So for approximations derivative, AD, by using the approximating the linear constant coefficient to find the differential equation. For IIM, we are using the specific n to find our HAS, transfer function in analog. For the BLT, we are using a specific n to find our pre-wrapping analog frequency omega. So which means you're using the equation 2 divided by t tangent omega divided by 2. So for the second one, for the AD, we are select the sampling frequency of the t second per sample. Same go to IIM and same go to BLT. For AD, we didn't use any equation to represent our HAS, but for IIM and BLT, they have a specific equation. So for IIM, we will have HAS, it will represent in summation from I equals to 1 until m, and we have a AI, A is our coefficient, divided by S minus of pole PI. For the BLT, we're using the analog frequency to find our HS. So this HS will be in B divided by S plus A. So by using these three methods, each method will provide the difference of the equation. So for AD, we will have S power of I. So 1 minus of Z power of minus 1 divided by T. The whole thing will power of I. So for IM, we will have 1 divided by S plus PK, and it will map to 1 divided by 1 minus our exponential PK ds Z minus 1 in analog, in digital. Then for BLT, we're using S equals to 2 divided by T, 1 minus of Z minus 1 divided by 1 plus Z minus 1. Last one, for AD, this design method only for the transforming analog low pass filter and band pass filter with the smaller resonant frequency for this AD. For IM, they are appropriate to design the low pass filter and the band pass filter with whose resonant frequency, any range of the resonant frequency. For BLT, normally we use for the high pass and the band reject filter to design these two. Okay, that's all. Thank you. So we